Okay, I think we're live. Interesting changes to the YouTube live streaming platform. I guess they've updated it. Oh, I can't talk. Updated it again. So, what's up, everybody? My name is Ryan, and today I'm going to be doing some work on implementing some data structures, particularly some node-based data structures like tree, graph, heap in particular. I have to kind of go through and see what I haven't implemented, and then I'll probably work on a few sort of data structures, a few algorithms for those data structures. Like if I get to graph, then I want to work on a BFS and a DFS. So if you're looking for like an introduction to data structures and algorithms, I've actually written an article on Free Code Camp, which is like an introduction to that. So I suggest you check that out. It's called How to Learn Software Engineering in a More Interesting and Less Painful Way. I think that's the name of it. So if you're a beginner, you're going to want to watch that. I'm not going to be stopping to explain the basics here. And this, I'm not sure how much value this will be, but basically the reason why I'm doing this is I'm prepping for some interviews in a large company. And so it's necessary to do a lot of work on a variety of data structures and algorithms. I find for me, I have a very poor memory for just like reading about them. But if I can spend a lot of time implementing them, then I find that's the way that I'm able to best learn them and also apply them in the context of an interview situation. So that's basically where we're at. So I'm going to get started. I don't anticipate a ton of questions or comments, so I might be a little bit slow to respond, but that's okay. Today's going to be a lot more about just getting the work done than rambling in the chat. Just give me a moment to get set up here. Also, I want to point out the main resource I'll be using today for the algorithms, just hints on them really, is Cracking the Coding Interview by Gail Lockman McDowell. Her book was strongly recommended by the company that I'm applying to, so that's one of the main reasons why I'll be using it. And then, consider checking that out. You can get it for free online, although, of course, it's always good to support the people who give you good quality content. So I wanted to start with thinking about tree problems. So I've already implemented a binary search tree, which is like basically just a binary tree, which has a particular requirement. And I think I'm going to now work on just some very basic tree data structures. And so not necessarily a binary tree. And working on, I think I'll probably start with just traversing trees to be able to count something like how many nodes have a given value or something like that. So that's what we're going to work on now. I'm going to make a new Kotlin class called Basic Tree. I don't think I'll bother doing a binary tree in this case, so it'll be a N-ary tree. The key difference between, say, a tree and a graph data structure is the tree isn't allowed to have cycles, whereas a graph will, but they're both basically composed of nodes. So I might not even bother with a class here. I think what I'll actually do, oftentimes you don't need like a wrapper class apparently, so I'm just going to create a class called tree node. Apparently I forgot how to write Kotlin. Yeah, we're going to create a class called tree node. It can be a data class, might as well. And it's going to have a value. For the time being, it's just going to be I think I'll probably just do ints. The idea is if you had some kind of a question come up, then you could adjust things on the fly. Like if I had to make one of these for a problem to do with strings, I could just make the value a string. Doesn't really matter too much. And that's one important thing I've learned is to just, let me think about this for a second. This is going to actually end up looking a little bit like a graph because I'm going to have, I wonder if I should make this a binary tree. I don't think I will. So, and I'll explain why that decision is important in a minute. So this is going to have, we'll call this children. I'm sure there's probably a better name for that, but we'll just go with that. And that's going to be a mutable list of node. And we'll probably just initialize this to an empty list. I don't remember if you have to say mutable empty list. I don't think so. Oops, tree node. All right. Mutable list of, I guess. Really? There we go. Hey, what's up, Arish? Must be pretty late in the evening for you. Oh, my second interview went quite well. I still haven't done my third and final round of interviews, but that's what I'm prepping for today. But my second interview, I actually think I did really quite well on the 2 coding problems that I was given, and my expectations were incredibly low. Okay, so now what I'm going to do is I'm going to create a main function. And the first thing I want to do is just write some tests. So I should think of some kind of an example here. So what I'm looking for, I want an example where I need to traverse the tree structure to count the number of elements. I think would be a useful thing to be able to do. Hey, what's up? I'm really sorry if I can't pronounce your name right. Oino? But what's up? How's it going? Internet cousin, yeah. You're all my cousins. And you know, science proves that we're all cousins, which is actually one of the main reasons why I say that. If you go back far enough, we're all cousins. Although I think I probably have some Neanderthal or Denisovan DNA. I've heard that a lot of people from Africa don't have that. I'm not sure how true that is, but yeah. Yeah. I'll call you Hudson. I'm sure I can pronounce that. Okay, so I want an example. Let's just make up a tree here, which is going to be kind of ugly on this thing. I might even draw something on paper because I don't know if I want to bother typing this whole thing out. So let's just... one thing I've learned when drawing trees and stuff like that, draw the numbers first, then circle and connect them. Tends to work a little better. 1, 2, 3. Do a 1 down here. Let's do a 4. I'll show you what I'm drawing in a second. 5. It's going to be a 2, 1, 6. Always good when you're doing DSA stuff. Work from examples. Kind of screwed this tree up a little bit, but whatever. Let's do one more 1 down here. Okay, so this is going to be the example that I'll work with, and I know my handwriting is terrible, or my drawing is terrible, both. I'll probably write an algorithm to like search or count the number of ones, or it might just be count the number of whatever integer I give to the code. That's probably actually a better way to approach it. All right. So now we need to build this example, and this will be a little bit tricky. I think I might do this kind of like from the bottom up, but we'll see. Excuse me. Let's do... I'm going to build this in kind of a weird way, but the reason why I'm going to do this is just so I can actually accurately recreate this thing. Left child equals tree node. And so let's see. Let me draw out the example. 1, 2, 3. Let's do 1, 4, 5. Oh, that's not what I wanted to do. Okay, and then here we have 2, 1, 6. And then we've got a 1. Let's just spread this out a little bit so that it's evident that's where that's coming from. Okay. So example tree. So that's the example. Now I'm going to try and build it out in code. So I'm going to do the left child here first. And then what we'll do is we'll add the left child first and then the right child. So for left child, it's got 3 of its own children. The value equals 2. And then children equals mutable. Technically, it doesn't really need to be a mutable list, but I think in some practical problems it might have to be, so that's why I'm doing that. In any case, it's not a big deal. And then we'll do tree node. This one will be 1, and we'll just do mutable list of. Probably need to give it the type. And I don't know why it's complaining yet. I guess we'll see. So this one's 4. This one's 5. Let me see why you are complaining. Oh, it's probably because I have like this default value. No. Does it need the type tree node? Mutable list of... Oh yeah, this is the wrong type. That's why it's complaining. There we go. All right. So I've got the right numbers here, 1, 4, 5. I'm just going to copy this whole thing and we'll just rewrite it a little bit. This will be right child. One of the most important things in data structures and algorithms, from my experience, is that one of the first things you should do is you should really get a handle on what are you giving to the function or algorithm you're writing and what are you getting out of it. And I find just diving straight into the implementation is a really bad idea most of the time. This one is going to be mutable list of, and we're going to give this one its own little tree node. Happy little tree node. That's a Bob Ross reference. Okay, and then we do mutable list of. Oh, and I can just do that. Can I remove that? Oh, nice. The beauty of type inference. Let me just clean that up all over the place, because in a coding interview situation, you want to practice having the most concise syntax. Okay, 3, 2, 1, 2, 1, 6. Yes, okay, that does appear to be accurate. And then finally, so I'm actually going to just minimize those two things. So we get some screen real estate, and then I'm going to say val root equals tree node. And what's the first value? 1. And then I don't remember off the top of my head what is a, or I think we can go mutable list of, and then I can just give it left child and right child. I think that will work, yeah. Okay, cool. So we have our coding example, which is kind of the first thing I wanted to take care of. So that's good. And so let's come up with some problems here, because life's just full of problems. So I'm going to make a new file called find actually no, we're just going to do it right here. Never mind. Since I've already bothered to set it up that way. Hudson asks, where is the left child and right child coming from? I'm just kind of making it up. Like by left child, I'm referring to this thing, and right child, this thing. Don't take it too seriously. The reason why I bothered to do this was merely so that I could just have an easier time making sure that I'm accurately recreating this example. If I had just done everything in like a single bunch of mutable list things, it just would have been a lot harder for me to keep track of, which is a personal quirk of mine. So it was really to just, yeah, make it a little more legible for my own sake. Because one thing that's annoying is you don't want to go ahead and code up an example, and then your example the code doesn't reflect the drawn up example, because that can be a really ugly situation. Okay, so I think for the first problem, maybe what I'll do is we'll write some helper functions to just clean this up a little bit. No, they are not. They're not inbuilt methods. Really, everything you see in here is really just from creating this single tree node. Okay, looks like we're on the same page. Find all occurrences, and we're going to give this our root tree node, and this is going to return an integer containing the number of occurrences. So what should our first test be? I think I'll want to test where we're counting the number of ones, so we'll say val find all ones test equals root dot find occurrences of find, I think I misspelled occurrences, find occurrences of, and we will give it our actually I don't think we need to give it how should I do this? I think, yeah, should I include it as a class within tree node or not is the decision I'm trying to make. I don't think I will. I think I'll pass the tree in. Fairly inconsequential decision to make there, but what the hell? Okay. Yes, create function. I like how it thinks I'm giving it an any. Oh, in fairness, that's my fault. I can't blame the autocomplete for that screw up. So this would be an integer. If none, if no occurrences, obviously return 0. That should be a proper comment there. Okay. And we need the, what should I call this? I'm going to call it value. Tufikas, is it sunny out there? No, outside it's minus 7 degrees Celsius and it's snowing periodically. It's quite warm in my apartment though. I live in Canada. Okay, so find occurrences of 1. Let's just add that in. So I'll say value int. Find non-existent. So we're gonna do 43. That's actually my favorite number, believe it or not, 43. And yeah, I think that's enough tests for now. I don't really need to go crazy here. So answer val answer 1 equals, I think there's 3. Yeah, 1. No, there's 4 ones. So answer 1 equals 4. Answer 2 equals 0. And then what we do is we say print line. No, we say if find all ones test equals answer 1, then print line success. Let's try that again. Else print line, otherwise I want to print what was the actual value. I need obviously 2 equals there. And then we have find non and answer 2. Okay. All right. Cool. What else are we getting? Oh, you're from the Netherlands. Goedendag. I don't speak much Dutch, but I know it's a language with a lot of so goedendag. For others listening, I just said good day. Okay. Aus Deutschland. Ich spreche ein bisschen Deutsch. Okay. Enough accents. So find. All right. So normally what I would do is I would like run this and make sure it's compiling. But in the context of these interviews, you very rarely get the benefit of having a compiler, so I'm not going to do that. However, I will fix this up. What's the problem here? Huh. Oh no, adjacency list. Okay. So, basic tree. All right, now we're going to get started. So find occurrences. So before I begin, I want you to keep in mind I'm making these algorithms up as I go here, so it's going to take a little bit. Let me just find some scrap paper. All right. So, find all occurrences. So the first thing I'm going to do is I'm going to look at the example. And how to traverse. So I'm going to get a few hints from the book I was talking about, partially just so I know what to call these different algorithms. So I need to search every node. And I think I might need a list to keep track of which things get which nodes get visited, or I might not. Okay. I guess I could probably do this sort of recursively. I think I am going to do this recursively. Now what I could do, I think instead of here, let me say what I'm thinking here. I think I'm going to recursively visit every node. Now that's a binary tree in the example they give, so I wouldn't be able to do it exactly like that, but that's okay. I think I can figure out my own way to traverse this thing. So I'll recursively visit every node, and I think every recursive call will return an integer. And if the value matches, it'll return a 1. Otherwise, it'll return a 0. And then I think the end result should be that I return the appropriate value. The other way I could do this is I could like have some kind of global variable that gets incremented, but I would say recursion is not really my strong suit, so it's probably something I should work on. So I'm going to work on a recursive approach. So from my limited experience with recursion, you always want to have a base case. And to me, the base case would be if a node has no children. I still need to be careful. So I think the first, I think I'm ready to start writing out my plan here. So number 1, starting with, I'll zoom in a little, starting with the root node and for all nodes. I like to write out my algorithms first in sort of pseudocode. So check. So let current be the node within the current function call. If current has no children, then return only if it equals the searched value. I should add that in there. Let value be the searched value. I've been really Hudson asks, I hear the word recursion a lot. Could you mind touching on what recursion means? Absolutely. If you have a few minutes, let me write it out, and then it'll be easier for me to explain. So if you can stick around for a few minutes, I will certainly do that for you. It's just easier if I actually write the recursive function. But in a nutshell, it's a function that calls itself. But that's just for me, it's easier to understand that in code, and it might be the same for you. So let value be the search value. If current has no children, then return only if it equals the search value. If current has children, call find occurrences. I should be more specific here. Add sum of all calls to find occurrences of for all children, and as well as ... We're just going to do some dots here, as well as this part here, if it equals the search value. In which case add 1 or return 1. Let's say add 1. Okay. I think that should pretty much get us where we need to be. I should be more specific here. Return 1. 1 only if it equals the search value, otherwise 0. Okay. So one tip I can give you right away, Hudson, similar to like an infinite loop, in recursive functions, you can run into a situation where a function is just endlessly calling itself. The way to avoid that is to have what's known as a base case. And let's start there. So we don't actually need to write, our value is already here. So we'll jump into here. So current equals, this should actually be current. Shouldn't be tree. And the first thing we'll check is if current.children.is empty, and that'll be one execution path, else. And we can do a return if, just to make it a little, some syntactic sugar. I'm just going to type 0 and 0 here so the compiler stops making the text ugly. And so if current.children is empty, if this is empty, then we're going to say if value equals current.value 1, else 0. And that's all we're going to do there. And then down here we're going to say else. And this is interesting. I've never actually done like a off the top of my head, I'm just trying to think of how to do this. So return so val has occurrence equals, and we're going to do this same code here. I feel like what I should do just to make this slightly better is we're going to say val has occurrence equals, just being a real stickler about having good quality code here. So we're going to return has occurrence plus, and then I'll need to figure out how to add all of the recursive calls. I'll just have to think off the top of my head how to do that. That free code camp algorithm power. So what I need to do is I need to be making calls to find occurrences of, but I need to do that for every child. I might need a counter. I might change my mind on this. I'm really just making this up as I go. Equals 0. And then we can say, I think what we can do is we can say children dot for each. This is weird because I feel like I'm doing both an iterative and a recursive approach, which is kind of weird when you think about it, at least to me. And this would actually be current.children. Not entirely sure this is going to work, but we're going to try. And then I would call find occurrences of so this would be it and value. And then we would say occurrences counter plus equals plus occurrence counter. I feel like I just made a solution which is both iterative and recursive, which is really weird. This would look a lot cleaner if it was a binary tree. If it was a binary tree, I would just go like occurrences counter for the left one and then occurrences counter for the right one, but it's not a binary tree, so I can't do that. So let me just make sure this code works, and then I will explain a bit about recursion. In theory, I think this should work. Has occurrence counter, but it might not. I'm really bad for misspelling occurrence. It Just really doesn't feel like a word that should have two R's. Yeah, let's run the code and see if it works. Okay, it works. Cool. All right. So that's important for me to note. Okay, so just a quick overview of recursion. So as was mentioned in the chat, a recursive function call is really any situation where a function calls itself. And it's an interesting little topic. A lot of problems in programming can either be solved using things like iteration, so like a for loop, loops essentially, or they can be solved by recursive function calls, so a function calling itself. In either situation, we can think of the loops as every loop is a frame of execution. In the case of recursive function calls, every function call in this stack of recurrent function calls is also a frame of execution. So they're loops and recursion, they're a totally different way of writing code, but they have this thing in common where if you need to break down a problem which requires this repetition, then they can often both be used to solve it. Personally, I find it a lot easier to mentally think about loops, or another word for loops is just iteration. But with that being said, it's really useful to be able to write recursive function calls, because I'm pretty sure this problem would be trickier to solve with loops. Off the top of my head, I haven't thought about it too deeply. So that's basically, hopefully that's a kind of basic introduction. I want to show everyone watching, and by the way, this is Cracking the Coding interview. This function would be a lot cleaner. I think this is kind of what I based it on. This would be a lot cleaner if it was a binary tree. In a binary tree, you've only got a left node and a right node for every node. So I wouldn't have to do this weird iteration thing looping through all the children. But that's okay. All right, so we have find occurrences of. I'm not sure if there's anything else I really want to do. Oh, let me just log out of Steam here. The other examples in the book are pre-order traversal and post-order traversal. I'm not particularly interested in implementing those. I see the only meaningful difference is just the order in which things are called. And I feel like I could come up with that off the top of my head. So I think that's pretty much, I'll leave off trees here. And I think I'm going to move into heap data structure. And heap is one that's been giving me some trouble. And I'll explain why. Is this a... Yeah, it looks like I already did some work on this. All right. So let's talk a little bit about heaps. I'm also going to find my spot in the book, which might be useful. I see they actually use trees for heaps, which makes me happy because that's what I want to do. So let me ramble a bit about a heap. So a heap is a data structure which has some very useful practical applications. Like if you're familiar with low-level programming at all, you've probably heard the terms heap or stack. Stack is a much simpler concept and also data structure. I'm not going to say heap is really complicated, but the heap that I'm going to be talking about is also kind of known as a priority queue. And so what that means is when you add something to that heap, you need to adjust the other elements to make sure that the element with the highest priority, assuming it's I think a maximum heap, is always at the top. And so that can be, there's obviously solutions for it, but let me tell you about my issue. So I tried, oops, I just accidentally opened Spotify, which probably doesn't work. I've been hearing that it's out. Oh, it seems to be back on. So there's a way you can do, Hrishas, is this repo public? It's not now. I am planning to make it public at some point, but it's not currently. Anyways, one of the ways you can make a heap is that you can use an array for that. And how you work with an array heap is you have these mathematical functions to figure out where you are in the heap. It's almost like you're representing the an array as a tree data structure, a binary tree data structure, I believe, or maybe even a binary search tree. Anyways, I don't like using the array because one thing I suck at is I'm not good at arithmetic. It's very easy, or much easier, for me to work with something like this where I can visualize things actually moving. Whereas if I try to do that in my head with just an array data structure, I have a lot of trouble with it. Apparently the rationale behind using the array is that it's slightly, or depending on the size of the data set, a significant amount more efficient. In terms of runtime complexity, it can be. But my plan for this interview is, or the coming interviews, is if I get asked a question about creating a heap or priority queue, I'm going to implement it with trees. And if they, I will probably bring up, I realize that in some situations it may be more efficient to use an array. I just personally find it a lot easier to work with a tree data structure. And the interviewer can kind of take what they will from that. As long as I solve the problem and it is an efficient solution, I don't think it should really be an issue, but we'll see. Just give me one moment, folks. Just going to get some water. My mouth is pretty dry. Okay. So it looks like I made a little bit of progress, but I'm not actually sure this is how I'm going to represent a heap. I'm going to take a look at the thing over here. So yeah, I think I'll probably work all right. Interesting. So I'm going to work on insert and I don't like the name of the functions they have here, extract min. I think what's the heap? I think the term they use is poll. Yeah, I think I'll use that particular function name, poll, P-O-L-L. So I am going to, I'm not sure. I don't think this code actually worked, but I'll have to just double check that. And then I'm just going to start from scratch on that. All right. I'm just trying to think if I want this sort of wrapping data structure or I just want like a root node. Also, where's my node here? Okay, left, right. So this is a binary tree. Okay. All right. So as before, I'm going to start with an example. I might actually I'll use a pretty similar example to the one I had before. Because I'm lazy, also known as efficient. And obviously it's going to be a binary tree, so we're not going to do that. Whatever, that's good enough. Okay, and then get me the example. Okay, so we got rid of the one. What else did we get rid of? We got a 3. I think that was 216, so we just have 6, 2, 4, 5, 1, 2, 4, 5, and then 3 and 6. 2, 4, 5, 3, and 6. Okay, that looks about right. Obviously, I need to change the type here. So this is going to be just to avoid naming conflicts, I'm going to call this a heap node. Let me just do that a little more intelligently. We'll do Shift F6, heap node. Okay. Okay, and then instead of doing that, we're going to say, so this will be left. Oh, that's not what I wanted to do there. And this will be right. Do I have to, why would I have to import it? Oh, there's something else called heap node. Apparently that wasn't a good name. Really? That's kind of blowing my mind, to be honest. Okay, what if I define it up here? Okay, I guess I gotta name it something else because the for some reason it's just not picking up that. Actually, maybe what I can do is I can maybe if I specify the type. No, okay, I've got to call it something else then. That's annoying. Let's call it my heap node. And it's still being annoying. Why would I have to... I don't get why I would need to import that. That's really weird. Oh, I guess because it's a child of Heap. Okay, that makes a little bit more sense now, actually. I get it. I was just wondering why I had to have the whatever you call that, qualified name. I really don't like that. So I'm just trying to decide if I want a I think I'm gonna define this outside just to get rid of that crap. Hey, was geht ab, mein Freund? I haven't had the chance to test out your Chrome extension, but and unfortunately for me, I don't actually get very much traffic, so I don't have a lot of comments, but I'll see if I can test it out sometime. All right. Now we'll call this heap node. All that work I just did, we're gonna do. All right. Heap node. All right. Hopefully that'll work. I'm just gonna comment this out here. But yeah, how's JavaScript going? Or have you tried TypeScript yet? Heap node. Okay, so left is 4, right is 5, so this is value equals that. Value equals that. I did a little bit of work with React and I liked it. It I think one thing for me which took a minute to sort of get used to was when I was doing it, maybe I was doing it wrong, but for like handling events, you had to like pass the event handler functions like all the way down the React components. But I actually feel like having had that experience, it made it easier for me to work in Kotlin Compose because I find myself having to do exactly the same thing, like passing event handler functions and stuff like that all the way down these chains. But oh yeah, I didn't see your comment until now. But yeah, I did same. I found some similarities. Why is it complaining? I think I should just give these, I should initialize the heap nodes to null by default. That way I don't have to explicitly do that every time. Okay. And what's going on here? Get rid of that. Yeah. Yeah, I got to be honest. I did not really like web programming without React. um, I could probably get used to it, but yeah, it just seemed easier to work with. So let's see, three, and then the right child of 3. I don't think I can do that because I think in a heap you're always supposed to add to the top down left right kind of thing. So I think this would actually have to be the left child. I need to make sure I do that properly. Is that how you do that? Rightmost spot. Okay. I've never personally tried PHP. I know it's still quite popular though, despite a lot of people making fun of it. PHP to me kind of sounds like the Java of the web web development world. Although I realize Java is used in web development, but I mean like front end. Okay. What I mean by that statement is that a lot of people complain about it, but it's still giantly popular. Okay, value. Sorry, I should focus on my coding now. So left equals left child, right equals right child. Okay, cool. Value equals 1. All right, that cleans that up. Now I need to decide if I even want to bother. I think I will have some kind of wrapper class. A lot of times you don't need it. Like if I was building a graph, I don't think I would. There are certain use cases where I might want to. If I wanted like a hash table to look up nodes specifically, but yeah. Howdy says, I was hired as an Android developer and had to work on PHP 8 upgrade. That sucks. I mean, I guess, you know, it's a paycheck, but that sucks. Hopefully you enjoy it. From what I gather, probably you don't. What kind of language? I've never seen a line of PHP. Is it like object-oriented or declarative, or what kind of language is PHP? And now I'm going to shut up for a minute and start coding here. Also, I'm going to move this example to the top because it's bugging me that it's down there. So I've got my example heap, and I'm trying to think of how I could actually meaningfully test this thing. I think like maybe actually printing the heap would be a good start, which I could do with like just a basic, what do they call that? In-order traversal. So I think that's probably where I will start. So we'll go with that. Oh my God, it's like Python with Java syntax? That sounds insane. Cause like I have written a bit of Python. I find it pretty hit and miss, but wow. Okay. Hopefully it's the best of both languages, but it really doesn't sound like it. Okay, so we're going to start with an in-order traversal. Or is that what they call it in this stupid thing? Yeah, in-order traversal, which is a fancy way of saying we're just going to print let's actually give it a normal name. Print all elements in order. We'll do it that way, and this will be pretty easy. We'll just give, so current, which is a node. This thing doesn't need to return anything, so that's fine. This is a heap node. And then so if how do we do this? If heap node, can that be null? Okay. If this equals null, then let's actually just do it this way, not equal null. Then that's, sorry, current. If current does not equal null, then we say print line current dot value, print line current dot left, print line current dot right, and then I feel like I'll need line breaks or something, but let's just see what happens when we call this. Okay, apparently I didn't say value. Oh, I just said print line. That was dumb. Oh, I guess you're supposed to have this one in the middle or something. How do you feel about Android, Florian? Pretty bored of it, or? Not actually sure if you're still there, but okay. In my case, I'm becoming that curmudgeonly developer that just like hates new libraries. I never thought I would become that guy, but I used to think like the key to becoming the key to becoming like the best developer ever was to like always be on the cutting edge of the latest libraries. Like as a junior and intermediate developer, that was kind of my what I thought you were supposed to do. And nowadays I'm just like, oh god damn it, another new fucking library. Oh cool, looks like you got something you're working on. Was it like a Pomodoro timer? Okay, so I want to see now, did I print that properly? It looks weird, but maybe this is... So it should be like one... Yeah, that looks weird. Did I screw something up here? Oh, nice. I don't know. So this is one of the classic problems. I need to be able to just verify that this thing looks like it's supposed to. I'll have to actually run through the code a little bit to just figure out what's going on here. Okay, so we start at the root, which is 1, right? Root node is 1, yes. And then we do our traversal down here. So the first thing it's going to print would be, I want to say the rightmost element. No, leftmost would be the first thing it prints, I think. Yes. Okay, so it prints the leftmost. Okay, I kind of see the pattern now. So it goes here, and then here, and then here, and then here, and then here. So it prints them from left to right. Is that what we're supposed to be doing? Have a good night, Hudson. Hopefully you have a good time at work. Okay, that is apparently what it's supposed to do. Pre-order, post-order, whatever. Okay, well, I'm relatively satisfied that this is doing what it's supposed to be doing. Yeah, that makes sense. So it goes all the way down here, prints that, prints that, prints that. Okay, cool. So why did I want to figure this out? The reason why is instead of asserting values for these tests, I think I'm going to just print the print the result and then see if it looks like what I want it to look like. And the reason why I would do that is just in this particular case, I feel like it's more straightforward it's easier to verify that, because otherwise I need to create this giant tree as an answer. And I guess I could do that, but then I need to be able to verify it. And yeah, I'm not going to do that. Maybe I will later. We'll see. Okay, so the first thing I want to do is I want to test this add function, and judging by this, it probably doesn't work. So I should probably figure out the actual algorithm. We'll call this insert, actually. And I have a relative idea, but I'm going to definitely use the book for reference here. All right. Insert. Is this a min heap? Yes. This is a min heap. All right. Important distinction. Also, I have this comment here. This heap doesn't grow, so don't add more damn numbers than you should. I don't think I actually need that because it's just a tree. We're not doing the array thing, so that doesn't apply anymore. So we're going to figure out our insert algorithm here. All right. So, according to the book, ja, auf Wiedersehen, mein Freund. Es ist Zeit für Schlafen gehen. All right. So it seems like there's two primary elements to insert. So the first thing is insert at the rightmost element of the tree. Yeah. We got a night owl here, 4 a.m. I think if I stayed up until 4 a.m. I would die. I usually try to go to bed around 9:30. This is definitely one of those streams where I did not anticipate having high viewership, which is okay. Sorry there's a lot of dead silence here, but I'm just trying to make sense of the steps for this. So insert, there's two macroscopic goals. So number one, insert at the rightmost element of the tree, which would be here. And two, basically heapify, they call it. I don't like that term, but whatever, heapify i.e. fix the tree so that it's, what do they call that? It's invariant, it's relationship. Property, that's what. Min heap property, and I should specify min. See you later. How do you sleep well? Min heap property. The smallest value is the top of the heap. Okay. So insert at the rightmost element of the tree. So how do we do that? I'm just thinking off the top of my head. Let me get my pen and paper out. One, 2, 3, 6, 4, and 5. Okay, I drew my example here. It's easier for me to think on paper. So how do I find the rightmost? I guess we would just keep looking right. So is it as simple as that though? So I think if left child is not null, if right child is not null, go to right child, I think makes the most sense as our first rule. I might change this later, but I'm just working through the problem here. So beginning the root at the root element. Let's say this, let current be the root element. This is pseudocode. Let current be the root element. If current dot left, actually I'm not going to do this that close to code. If left child of current is null, sorry, is not null, left and right child of current, children of current are not null, then I think we're going to need something recursive here, almost certainly. Insert, so we're not going to do it this way. So what we would do, we'll have an insert which passes in the value. And then we're going to have another insert which is private. And it'll have current, which is a heap node. And then value. Okay, I think I like that. So if the root in this heap is null, we can be assured that the first value will be the top of the heap. So that's cool. Otherwise, we're going to call insert with root as the current and value, obviously. Why is it complaining? Because root hasn't been created. Oh, because it could be null. Well, in this situation, I know it's not null. So, all right. And why do I know it's not null? Because we're not dealing with multi-threading here. Okay. So what we'll do now, it's going to actually start with, I think probably essentially the same thing. If current equals null, current equals heap node with the value. It's always false. No, it's not always false. There we go. Oh my gosh. I think we're actually just going to do this. Let's do that. Okay. If current equals null, then current equals... Oh, but I can't do that though, because I need to assign root, which is why I can't do that. Yeah. Okay. Why is it complaining? If current equals null, current equals heap node, whatever. Why is it complaining? Val cannot be reassigned. Oh, yes, of course. That's a problem. That is a problem. So in Kotlin, parameters are value types, so they can't be reassigned. And I had forgotten about that. So I have to figure out a different way of doing this, basically. So I might have to do this iteratively. I think I'm going to try and figure it out recursively, though. I think what I would do is make this not nullable. And I can assign, I don't think the children are not values. So what I can do, we will assert that, and we'll do it this way. So we've satisfied the condition where root is null. Now we're only at a bare minimum here. We are assured that root is not null, and then we can work with the children. And then we can deal with our stuff here. The approach I was using before makes more sense now. Okay, insert at the rightmost element of the tree. Sorry, I'm going to have to shut off my studio lights here. They're starting to bug my eyes. Okay, that's better. I don't need my headphones. Okay. Insert at the rightmost element of the tree. So if left and right are not null, then insert current dot right. That makes sense to me for now. If both children are not null, we're trying to insert in the rightmost element. So I think we'll start there. So when current dot left equals null and current dot right. Sorry, I think it's not null. Yeah, not equal null. Not equal null. Okay. Then we would just call insert current dot right and value. Okay. Why is it complaining? Oh, and we can just assert that. Okay. Assert non-null. So that's the first situation. So we go to 3, and then we see that the left child is not null. the right child is null. So there we would add to the right child. All right. That's pretty straightforward. So when current dot left is not equal null, and current dot right equals null, then current dot right equals heap node. No, heap node with value equals value. Okay, cool. And then in the final case, left equals null. Or we could just do an else. I think we'll probably just do else. Okay. I think that's pretty much it. Yeah. So what I'll do next is I'll test it. So I'm going to copy this and we'll say, oh, that did not copy well at all. So we'll say test 1. We'll be adding a 7. Okay. So then what we'll do is we'll call, so we'll say, we'll keep that there for now. No, we won't. We'll say, root, no, we create our heap. Oh, I don't know how well that's going to work. So I'm not actually going to be able to do this the way I did the other test. So instead of actually building out the structure, we're going to have to just insert everything. So that can be our first test, just making sure that we end up with this as our result. So so that's going to equal a heap, and then we'll call heap.insert. And what I'll try to do in this case is I'll try to actually just insert them in the appropriate order. So 1, 2, 3, 4, 5, 6, and I'm getting a little tired, so I'm not even sure if that's going to work properly, but let's see. I'm going to create a function get top element, and this will be a function which just returns it, but it doesn't actually remove it from the heap data structure. I'll just make a note. So this will return a nullable heap node. And we can do single, what do they call that? Single expression syntax. Okay, get top, heap.get top element. Okay, let's see what happens. Okay, so I don't really think that worked. Let's look at how we are inserting. So we start with a 1, and that becomes a root. Then we get a 2, and what happens? We get a 2, and we're looking at 1, and we see that current.left should become, yeah, that part looks correct, because both are null. In the next iteration, we're given a 3. We start at 1, and then left is null. I think I might have an error in my logic here. Left does not equal null, because that's now 2. Right does equal null, so we set it up as right. Okay, so that makes sense. So why are we getting 2 as the first element? That's very weird. All right. And then we get a I really feel like I should be calling like insert. I think I'm missing a call to insert. Let me think about this. So current.left does not equal null. Current.right does not equal null. I think this is a false assumption here. I'm always assuming that if both are not null, that you would go right, but I don't think that's a correct assumption. Looking at it, I think it might actually be the opposite. I would go left. I don't know. We'll see. All right, folks, I think I've been going for about 90 minutes here, and my brain is starting to slow to a crawl. So I think I'm actually going to call it a day for live streaming. But yeah, to anyone who actually watches to the end of this video, you must be masochistic, or you enjoy listening to me ramble. But in any case, I applaud you, and I hope you have a great day. So that's it for